Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
So last time we were doing various ways of getting confidence intervals for a number of situations. I want to emphasize that the thing I did at the very end last time, which was talking about two samples, so this is kind of so important. Let me say estimation for mu x minus mu y. It's so important that I'll review a couple of the things. The first thing was, I'm sorry about the error that you would have seen last time. I kept doing things of the form difference in means. You can't see it. Autofocus. Yeah. I kept doing things of the form difference in mean divided by some estimate of the standard error. So, one of the most important formulas was this one. Now, I said that this has a t distribution, n plus n minus 2. That's not true unless the means are the same, because, of course, the expected value of x bar is mu x. Okay, in case you forgot, x1 up to xn IRD normal mu x sigma. Okay, so for the moment, let me focus on the equal variance case. Because that's kind of a better, more satisfactory theory. It's very exact, sigma squared, and that's independent of y1 up to. So this is two independent sample case. If you have two paired samples, that's totally different. You probably remember that from first year. Then you subtract xi minus yi, because if they're related, you just assume that the difference between them is 0. So that's different. But in the independent sample case, you just assume that these guys are independent of y1 up to ym, which are IRD normal mu y, comma sigma squared. So key point is that they have the same variance under this assumption. Now, I'm afraid I wrote this last time. Obviously, unless mu x equals mu y, then the top part is not a mean zero normal. The expected value of x bar, as you know, is mu x, and the expected value of y bar, as you know, is mu y. So I have to subtract, in order to get something to mean zero, I have to subtract off mu x minus mu y. Now, at the end of the course, chapter 10, we'll talk about hypothesis testing, and then very frequently your null hypothesis is that mu x equals mu y. In that case, you would have a simpler formula for the t statistic. But here, I'll call it capital T because it's the thing that has a t distribution. That t statistic has to subtract off the true difference in mean. Okay, so now that is a fact where the pooled variance, P stands for pooled, is of course, well, you know, if you know the sample variances, you just do a weighted average of sample variances, and the weights are by the degree of freedom, not by the actual sample size. As usual in this case, the degrees of freedom for a sample are the sample size minus 1, because you've taken out one degree of freedom to estimate the mean, you have n minus 1 remaining. So that's a fact. We pretty much proved it last time. It might not have been super clear. So the proof that it has that distribution is, well, certainly x bar minus y bar has a distribution normal subtract the means, x bar and y bar are independent, so when you add or subtract independent normals, you subtract the means, you add the variances, sigma squared, and sigma squared is the same, in this case, sigma squared over n plus sigma squared over m. Okay. So it's the same sigma squared for both of them. So when you do x bar minus y bar minus mu x minus mu y, subtract the mean divided by the variance, divided by the standard deviation of mu, 1 over n plus 1 over m, as of course the distribution normal 0 to 1. And all I've used in random terms, mu x, mu y, and sigma are constants. All I've used in random terms in that expression, no, that's not the same as this expression. That has a sigma instead of an SP. The only thing I've used is x bar and y bar here. And just remember that four-way trinity, not trinity if it's four-way. All these four independent things, s squared x and s squared y, so I don't quite know what I'm doing with that. But all of those are independent. That followed from our big theorem. So the pooled is some combination of s squared x and s squared y, but it's still independent of the x bar and the y bar. And so, independent of all that, and let's just say, it's not hard to check that this has a chi-squared n plus m minus 2 distribution. You have to, of course, scale it sigma squared over n plus m minus 2. Okay, so that's what the distribution of that guy is. And then, therefore, all I'm dividing, I take this, which you could call that z. Z's a common name for a normalized, standardized normal variable. And then I'm dividing by a certain ratio. The ratio that I'm dividing by is SP over sigma. So T in this context is going to be Z over R. Okay? And so, of course, Z is the normal. R should be square root of a chi-square divided by its degrees of freedom. Well, lo and behold, this is the square root of this chi-squared n plus m minus 2 over sigma squared SP squared. That's the chi-squared. And so all the multiplying and dividing by the same number of degrees of freedom. I don't know if T is here, but n plus m minus 2. So that guy is a chi-squared n plus m minus 2. And I've divided by its degrees of freedom. So it follows from the definition of T. We didn't calculate the density of T yet. We can do that later. It's quite, just uses the standard transformation techniques that we used. But we did have the definition of T, which is that a normal divided by an independent R, which is square root of chi-squared divided by its degrees of freedom. So that definitely has distribution in T n plus n minus 2. Okay, so much is exact, and then you can use that to get the confidence interval that we talked about last time. And as a reminder, that is for mu x minus. It's not going to give you a confidence interval for the individual means. For that, you would use the one variable setting. So you do x bar minus y bar plus or minus a quantile of the t alpha over 2 minus 2 times the standard error. Standard error is just the thing you have in the denominator, SP. So it's easy to check that. 1 over n plus 1 over n. That is your 1 minus alpha. So we've pretty much reproved everything about that modulo the big theorem on this page. So that's a bit of a review, and just remember that you have to subtract the mean or the difference in means. So the unequal variance case, and I just want to reiterate that this. Okay, what is what unequal variance means? It's the same except xi is IID normal mu x sigma x squared. So they do all have the same variance within the x's. That's not unequal because the xi are IID. But the yj's are IID nor mu y sigma squared 1. Now, in this case, you can't actually do an exact confidence interval. It's too complicated. So that's sad. There will be this approximation, which I'm not even going to write it again. We call it the work-satisfied approximation last time, and it's not examinable. But I want you to know the key fact about the degrees of freedom is that it's at least the minimum of n minus 1 and n minus 1. Now, why would it be n minus 1? So why would it be useful to know that the degrees of freedom is at least something? Well, that doesn't help you to get an exact value at all. It doesn't help you to get an exact value. What it does help you is to give a conservative confidence interval if you want to do that. A conservative confidence interval is one that it'll be a random interval, and instead of the probability of mu x minus mu y lying in that interval being exactly 95% or 1 minus alpha, it will be at least that. So your interval might be a bit wider than needed to obtain a certain confidence, and there's also a level of approximation in that. So for a number of reasons it's less satisfactory, but the one way in which it's more satisfactory is that it deals with this more general situation where they don't have the same thing. So there's a lot of theory behind that, and it was a difficult problem in statistics for some time. People came up with a good approximate solution, but for fundamental reasons, it's not possible to give the same exact solution. And this is called, the test associated with what we did before is called student's t-test, or in this case it would be student's t, statistic for a confidence interval. This is sometimes called Welch's t-test, or Welch's, because Welch was the guy who came up with this approximation. So conservative value for the degrees of freedom is just the minimum of these two. And the standard error, and to be precise I'll say the estimated standard error, is no longer with a pool of variance. There's no point pooling the variance if the variances are not the same. You're just estimating something that doesn't exist. The whole point of SP was you're estimating signal, which does exist in the equal variance case, doesn't exist in this case. So the estimated standard error is just kind of what you'd expect, Sx squared, square root of Sx squared over n plus Sy squared over n. Okay. So your 1 minus alpha confidence interval, which I'll reiterate is conservative, which means it might be wider than needed and you can't be really exact about that. Conservative 1 minus alpha confidence interval for mu x minus mu y. Now I probably need a name for this. Let's just call the minimum. I don't want to rewrite that minimum expression all the time. I'm just going to call that nu. Often we use nu as a Greek letter for a number of degrees of freedom. So, in other words, if one sample size is 10 and the other size is 12, you would take the minimum of 9 and 11, so 9. And in that case, your confidence interval, once again, x bar minus y bar, you get used to the rhythm of this plus or minus t, still alpha over 2, which will be the end point of it. Now, and then I'll do nu. So you notice nu is a lot lower than n plus n minus 2. So already, you're having a lower number of degrees of freedom in your t, that means a heavier tail. That means you would expect your quantiles to be further out. So this will be already wider just by having that t alpha over 2 comma nu. And it's wider effectively to compensate for the uncertainty of not knowing that the variance is the same. And although, look, I'm not always going to guarantee that in every single interval it will be wider because there may be something slightly different about this calculation of Sx squared over n plus Sy squared over n. Okay, so that's what it is. Since it's not exact, I feel that there's not a whole lot more to say about it. And I certainly haven't proved why this works or anything like that. But, and to reiterate, the well-satisfied approximation actually recommends a different value of degrees of freedom. It's just kind of too much bother to work out. It's often a real number, and depending on the case, it could be anywhere between the minimum of these two and anywhere as high as n plus n minus 2. So that degree of freedom will always be less than or equal to n plus n minus 2. So that's all I want to say about the unequal variance case. So the other thing that I advertised to talk about this time would be the ratio, and this one we can do exactly, of two unknown variances. So recall so just to remind you, what is a t distribution? This guy is pretty much the definition of a t distribution. A normal divided by an independent square root of chi squared divided by degrees of freedom. And now we're going to recall the definition of an f distribution, which is instead of, t is sort of like the one, when you have one dimension that you care about, which which is like the difference of means. So that's a one-dimensional thing. X bar minus y bar can only vary in one-dimensional space. If instead you're worrying about multiple differences at the same time, and you're sort of wondering whether all of those differences are, zero or not, or for instance if you're doing a variance, then you have a sample variance is effectively a multi-dimensional calculation. It's an n minus 1 degrees of freedom. So a t distribution is not appropriate for comparing two different variances. What you need instead is an f distribution, and it's if you've got, I'm going to say if x has a distribution chi-squared. I need to pick a number of degrees of freedom. Forgive me for using all these Greek letters, but I'll use nu for the first number of degrees of freedom. And if that's independent of y, which has a distribution chi-squared, what's the Greek letter after nu? Psi. So nu and psi will be the number of degrees of freedom. Then the distribution of, once again, we divide by the number of degrees of freedom in each case. X divided by nu divided by y divided by psi. If you're wondering why the division, it does actually make the formulas more complicated to put this division in it. The reason is it's for asymptotics. Particularly when psi goes to infinity, all the f, so this is the definition of an f distribution. It has 2 degrees of freedom, not 2 different numbers for degrees of freedom. The numerator degrees of freedom, which is nu, and the denominator degrees of freedom, which is psi. So we write them in that order: numerator first, then denominator. So that's the definition of what an f distribution is. F named after Fisher, very famous statistician. Although Fisher was not actually the first guy to talk about it, the name Snedeker comes up, and I don't really know the history. So if you care about history, then look up a book about that. But, it certainly dates back to the early part of the 20th century. It's very good for analysing these things. And yeah, so you have the divide by the degrees of freedom in the denominator. The reason is then if psi is sort of 100 or psi is 150, then the f3, 100 and f3, 150 will look almost identical. That's because, a chi-squared 100 is pretty much most of the time about 100. And a chi-squared 150 is most of the time pretty much 150. And it gets better and better as psi gets higher. So if you have psi very, very large, you won't likely have the correct value in your table. So by having this division by the number of degrees of freedom, that makes it much more suitable to use tables and much more suitable to reason about the asymptotic behaviour, because you don't have to make a correction. It'll just look pretty much, chi-squared with psi equals 100 will look pretty much the same as chi-squared with, chi equals anywhere around 100. And even, chi-squared with... and the other thing is, we'll talk about this a bit later under consistency. Remember, chi-squared is a sum of independent squared normals. So the expected value of y is psi, and the variance of y is actually 2 psi. Now, if you just think psi is really, really large, say psi is 1 billion, then y is expected to be about 1 billion with variance 1 billion, so standard deviation about 30,000. So that means as a proportion of the total, y will be, the variance of that is nothing at all. So, and in the limit, y of xi will just be exactly 1. So actually, as the limit, I might even say that, f nu psi, as psi goes to infinity, if you fix nu, the distributional limit of this is nothing other than chi-squared, what you had on the numerator, which is chi-squared nu, and I guess I've got to divide by that. So that's another thing. If you don't know, if psi is just huge, you can even get the f from a chi-squared table. Okay, so, and then it also follows from the definition, just a couple of facts that follow from the definition. And another fact that follows from the definition is that f psi comma nu has the distribution, same distribution as 1 over and f nu comma psi. For obvious reasons, right? Then the y of xi goes on the, if you take 1 over this guy, you've got y of xi divided by x over nu, and therefore it's the other way around. So this allows you, I'll even note this part B, allows you to find the quantile. You might want the lower quantile of a chi-square distribution, and normally the table, because there's so many mu's and psi's to pick from, normally they'd only give you the upper quantile, probably 95th quantile. So find the quantiles F. So if I want the 1 minus alpha quantile of, okay. So the convention which matches those tables I gave you will just be that F alpha nu psi is the probability that, so F is this thing, probability that F is greater than F alpha nu psi is equal to alpha. So this is the right tail probability. Now F, as you would notice from the definition, is always a non-negative number. I'll draw it typically like this. I'm not going to guarantee it always looks like that, but you know, that's a fairly typical behaviour with a bun. You know, depending on the value, you know, there's a whole lot of different curves, one for each value pair of nu and psi, but this is a typical one. And then that would be this right quantile. So the right quantile. So that would be F alpha nu psi. And then we might also, you know, of course alpha is often 0.05. We might also want the left quantile, and then that would be F1 minus alpha, comma, nu psi. So I have to tell you both degrees of freedom as well as the quantile I want. So how do I find F1 minus alpha and nu psi? The key thing is, you can't get it from the same degrees of freedom because there's no necessary relation. But you can say that for this guy, nu psi, to be less than the 5th percentile, that would mean its reciprocal, which reverses the order, is greater than the 95th percentile, right? If you're on the left 5% of this guy, then the reciprocal would be on the right 5%, and that relates it to F alpha. So the reciprocal of that is 1 over F alpha, comma, psi, comma nu. Now you see I've reversed the order of the degrees of freedom. So this one will often be in your table, and that's how you find those quantiles. So now, that's okay. So first of all, we just did the definition of F, and once again, you can calculate the density of that. I'm going to skip over here because you don't actually need the density to do these calculations. Okay, and then if once again xi, so this is the same setup as before, IID normal mu x sigma squared x, independent of yi, IID normal mu y sigma squared y. Then, of course, s squared x divided by s squared y. Well, we have to think about what each of those is. That's chi squared, except with a scaling factor of sigma squared x divided by degrees of freedom. And by the way, I'm not assuming the same number of variables here. So let's say that there's an I goes up to n, and j goes up to n. So that's the same as before. Okay. And then I'd better make a correction for that, because there is sigma squared x effectively in this sigma squared. So I'll do sigma squared y divided by sigma squared x. Okay. Now, by doing this, I have a pivotal quantity. The pivotal quantity has the distribution f. Degrees of freedom for x is n minus 1. Degrees of freedom for y is n minus 1. So that's this guy is pivotal. Remember, pivotal should include the sample, but it can also include the unknown variables, so long as you get something that is independent of the unknown variables, which that is. So, let's say 1 minus alpha confidence interval for sigma squared x. Once again, this will give you for the ratio. If you want the ones individually, you'd use the chi-squared method we did before. Well, since I don't know the formula straight off the top of my head, I'm just going to, it's got by doing the following thing. The probability that this observed quantity, has an F distribution. F is between F alpha, it has nu, so on. And I want F1 minus alpha nu psi, and I'm straight away going to use this formula that I've just done because that might not be in the table. So 1 over F alpha psi nu. So you see that one is different because it's got the degree of freedom in the other order. That is equal to, and that would actually give me both alpha and both. So let me make it instead alpha over 2 here. So if I want 1 minus alpha confidence interval, then I take alpha over 2 here. That would be a balanced one plus alpha over 2 here. And that's how I do it, is equal to 1 minus alpha. Okay. And I substitute in F to do that algebraically. 1 over F alpha over 2 psi nu. In this context, nu is the numerator of degrees of freedom, which is n minus 1. And psi is the denominator of degrees of freedom, which is n minus 1. So I'll do that directly here. So 1 over, here I have to do m minus 1, n minus 1, less than or equal to, substitute what f is, which is sigma squared y over sigma squared f, s squared x over s squared y, less than or equal to f alpha over 2 n minus 1 n. So both of those can be looked up in the table. Which would cost, if I want sigma squared x over sigma squared y, you just have to do a bit of cross multiplying to get this correct. So I'm not wrong then putting that. All these things are positive, so cross multiplying is not going to change the order of any inequalities. So that thing is equivalent to this, which is equivalent to sigma squared over sigma x over sigma squared y, is going to be less than or equal to s squared x over s squared y times this quantity, f alpha over 2 m minus 1 n minus 1. Now on the other side, same thing, sigma squared x over sigma s squared x over s squared y. This is observable, of course, times 1 over f alpha over 2 n minus 1. So that's your confidence interval. Lower down there, up and down there. And in a specific example, you could just substitute in known sample variance of x and y that can either be calculated or given to you, and you get those from your tables. So not so difficult. I just want to give you an example to show it's not always exactly the same. Let's say there's a better option if mu x and mu y are known. So typically, I guess they might not be known. But if they are known, it's always better to use more degrees of freedom if you can. And if you don't have to estimate mu x, then why not refuse to estimate mu x? So I'm going to introduce if mu x is known, the best estimator of sigma squared x is not actually s squared x. So I'm going to do a new one, s hat x squared. Okay? So I'll just say that this is a better estimator, and we can. It's not sort of hugely better, but it might make sense to use all of this if you can. There's some theoretical sense in which this is the best unbiased estimator in the case where you know mu x. So what I'll do is I'll just sum I equals 1 to n of xi minus mu x squared. Now you notice that xi minus, since mu x is known, xi minus mu x has mean 0. So I'm adding up n squared normals, each with mean 0. So this already should look very chi-squared-ish, except I should probably I want to make it unbiased. You see, the expected value of each of those summands is sigma x squared. So since there's n of them, I should divide by n. And then that is unbiased. Expected value of s hat x squared is equal to sigma squared x. But the distribution of this is slightly different from before. Instead of n minus 1 degrees of freedom, we have n degrees of freedom. And S hat y squared will be the same, 1 over m j equals 1 to n y j minus mu y squared as a distribution sigma squared y divided by m chi squared n. Okay? And those, of course, are independent. And so in that case, I won't go through all the details, but you could do a similar reasoning on the basis of the following pivotal quantity, S hat x squared divided by S hat y squared has, that's a pi squared divided by its degree of freedom, that's a pi squared divided by its degree of freedom. I better correct for the sigma squared, so sigma squared y divided by sigma squared x is a pivotal quantity, which I could call f in this context, but it now has a distribution f n comma n, not n minus 1, n minus 1. And the reason is, the minus 1 is 1 degree of freedom that was lost to estimating the mean. If you don't know the mean, you do have to estimate it, so you have to do it that way. This is slightly better because higher degrees of freedom always give you slightly more precision. Okay, so that's just a slightly different option. And you could even think of more variants of that. For instance, if you didn't know mu x and mu y, but you knew that they were the same, that's kind of an interesting question, but I won't do it now. So it's not to say that you always do it the same way, but that would be the most common, because most commonly you don't know the degrees of freedom. Okay, I want to go on to other sorts of interval estimation before we do. Basically, we're finishing chapter 8, which is some properties of interval estimation. Then we're going on to chapter 9, which is a whole lot more detail about point estimation. So to finish off chapter 8, I actually have to go back to something that's, let me just say what we've done pretty much. So we've done interval estimation, which basically means confidence intervals. By the way, those of you doing 6013 will learn about various Bayesian approaches to that, which are slightly different. You get credibility intervals and so on. That's not covered in the main intro to these lectures. But so for us, interval estimation is mainly confidence intervals. For means, variances, difference of means, and we didn't do it for difference of variances, we did it for ratios of variances. That's just something that's more simple to estimate. Let me say, independent normal samples. So, one sample or two. Each sample is IID, but of course they may be different. So that's what we pretty much talked about. But we have to talk about now the same estimates for proportions. So proportions, which is kind of a code word just for binomial, because if you think about an IID number of trials, each of which is success or failure, you just count the number of successes. So to talk about proportions, we just have to talk about binomial NP. And typically, when we're doing this, we'll imagine that n is known, so we're going to NP. And I guess you might also call it rate parameters are often used in Poisson. So the rate parameter is called. So how are we going to do this? Once again, we're going to hope to have an IID sample, and we're going to stick to the case where the number of trials is known. In the case of binomial, it's n trials, each of which is a yes or a no. Poisson, you're going to have n trials, each of which is a count data. So it might be n days, and on each day, how many people came into your shop, or how many. It may be more in a physics example. You've got n different time intervals, and on each interval, how many photons struck your receptor. So that kind of thing. Each of those is a random number, and we'll be trying to estimate the rate. So the first fact is that there is a normal approximation. The normal approximation would say relative to p, except it's not that n has to be much larger than p. That's obviously going to be true. It's that if p is really close to 0, then n has to be even a lot bigger, because it's hard to estimate proportions that are near 0. And if p is near 1, then it has to be a lot bigger. So I'm not going to say relative to p. I'm going to say relative to 1 over p, 1 minus p. Okay, that's just kind of a cop-out, which is to say that n p 1 minus p is a lot. So that's kind of an approximate state. What does that mean? Is it substantially? Now, of course, np 1 minus p is the variance of the binomial, so it's not going to be huge, but it's not, it's a decent distance away from 0. It's not getting really small. So normally the way you check that by now, I'd say this is a rule of thumb. It's of course not very mathematical to just get a cutoff, but I'll give you the reason why. So you check that np is at least 10. Now 10, of course, is a little bit arbitrary, but n times 1 minus p is at least 10. You might wonder, why not just check that n times p times 1 minus p is greater than something? Well, these are kind of better things to check. And they're better to check because this is the expected number of successes and that's the expected number of failures. And sometimes you don't know p, so in the case where you don't know p, then what you check is n p hat at least 10, and n 1 minus p hat is at least 10. Now what is p hat? P hat is the observed proportion. So whenever you have hat, it means something that, well, it usually means something you observe from the sample, so that would be k divided by n. Right? That's just the observed proportion. So if you don't know p, that's what you normally check. Now it is a rule of thumb, so it's not worth going into too much detail with that cutoff. But this is substantially checking the same thing as that, because of course if p is near 0, then 1 minus p is between a half and 1, and it doesn't make a big difference. We're talking in rough terms. So when 1 minus p is near 0, then p is bigger between a half and 1. So that's pretty much checking the same thing as this. So this would be your rule of thumb. And if so, it is reasonable to apply the normal approximation. Okay. The normal approximation, of course, k. So I'll do the plus one example in a little moment. K approximately normal. Now, of course, the mean doesn't change. The expected value of k is np, and the variance is np 1 minus p. Okay. Or p hat is approximately normal with mean p, p 1 minus p. Is that the correct variance? Someone think carefully. I've taken k and I've divided it by n. So the mean divides by n. Does the variance divide by n? Just to check whether you're on the same wavelength. I'll have to divide by n squared. Remember, there's two different operations. It's easy to think that the variance goes linearly in the sum. That's only when you're adding independent guys. If you add n independent copies of it, you get n times the variance. So we're used to that for normals. But if you're dividing by n, that's not dividing into n independent copies. That's dividing into n the same copies. And when you're doing scaling like that, real scaling, you get an n squared. Or in this case, we're divided by n, so we get divided by n squared. There was an n on the numerator, so the end result is p1 minus p. Now this makes sense. The higher your sample size, the less variance there is in your proportion estimate. So that's so far so good. And even we're going to get even a little more woolly about this because we're going to sometimes not know what p is to do a confidence interval. So we're just going to kind of guess, as you would imagine, and our best guess of p is p hat. Like if you've done a number of coin flips and you don't know the true proportion, or you've done a number of trials, you don't know the true success proportion, you only know p hat. So it's tempting just to put in p hat, 1 minus p hat there, and that's what we do. So once again, I'm not going to justify any of these things that well because there's so many approximations going on. All I will say is that mainly this rule of thumb is what's important. Now, clearly that's arbitrary. So why 10 and why not 100 or 1,000? So the answer is you would want them to be more than 1,000 if you were doing confidence intervals that were very far into the tail. So if you wanted a 99.999% confidence interval for a proportion, which rarely do you have enough data to do that. It doesn't make sense if you don't have enough data. But if you were trying to do that, you would actually need to check something much more stringent. So reasonable, let me fill this in. At typical confidence levels, we're talking about confidence interval, e.g. 1 minus alpha equals 90%, 95%. Probably could do it for 99%. I mean, as I say, all of this is a rule of thumb, so there's no real mathematical statement as to... You could give very precise bounds to how far off the approximation is, but it's too complicated for this course. So basically, you should just remember that that 10 is something to do with the fact we're throwing away 5% of output, so 5% of them will be wrong anyway. At that point, there's no point in insisting anything more than that. But it is important to have some restraint, because if p is 1 in a million, you're going to need a very large n before you detect it. Just think about that naturally. If you have a rare disease and it only happens in 1 in a million people, and you sample 10 people, or you sample even 100 people, you're not likely to get any useful information of the disease, because most likely you still won't have found anyone, so you just can't get any information. So that's the reason for those proportions. And the same if 99.9% of people have a condition, you need a very large sample size before you can tell anything about that proportion. Okay, so reasonable to be prime, normal approximation. Now, here's the thing. The probability of... for confidence intervals, maybe this doesn't matter so much. Later we'll talk about hypothesis testing, and then there's a slight issue with exactly where you apply the normal approximation, because this something that's interesting. Probability that k, you would have already seen this. Probability that k is strictly greater than some integer k, if that's a whole number. There's a whole number. That's exactly the same as probability that k is greater than or equal to k plus 1. That's because anything that takes an integer value can only take either k or k plus 1, nothing in between. But you could also do anything in between, and in particular, that's the probability that k is greater than k plus a half. So when you're doing exact binomial probabilities, all of those are identical, of course, you can calculate them the same way. When you're doing the approximation, if you just do this approximation, let's replace k by a normal that has this distribution, suddenly all of those three cutoffs will give you different values. So there is something called the continuity correction for normal approximation. And we'll do more examples of it when we do hypothesis testing. But the continuity correction, and it's called correction, it doesn't even always improve the estimate. Like you're going to get an exact binomial probability for all of those three are the same. There'll be three different normal approximations. The continuity correction claims that typically the best cutoff to use is little k plus a half in that example. In other words, if you're asked, is this greater than or equal to 11, or is it strictly greater than 10, or possibly is it greater than 10.5, the best one to use in your normal approximation is 10.5, because it's sort of halfway between. And that's a general rule of thumb. Once again, it's not always true. You can find cases, typically in the tail of the normal distribution, where it's actually better to use one of those two. But typically towards the center of the normal distribution, the normal curve is pretty flat towards the center. It's not, well, okay. It just turns out that it's usually best towards the center of the distribution to use that continuity correction. But for the interval estimation, we're not going to care about that. So, and I'm just going to say approximate 1 minus alpha confidence interval for p. If you don't know p, it will be... okay, so what is the setup for this? Observe outcomes 1 to up to n. So there are n outcomes, and each of them is a success or a failure. That's why we're talking about proportions. And k successes total, that's an observed statistic, and the proportion is p hat equals k. Okay, that's the observed proportion. Okay. Then the approximate 1 point minus alpha confidence interval, and the assumption is these are IID outcomes with the true success probability P. So that's what we're used to from binomial. The approximate 1 minus alpha confidence interval for P is, well, the reason it's approximate is that Z is, let's call Z equal to P hat minus its expected value, P, divided by square root. You see, P hat is normal with this mean and that variance. So now, it would be natural to divide by P1 minus P over N. Now, the problem is when you do that, you just can't solve for P. It's too complicated. You know, I guess you might get a quadratic and you can do it. And there are more sophisticated methods of approximating the confidence interval, so we won't go into those. But ultimately, there's always going to be some level of approximation. And the simplest approximation to do is this. I can solve this much more easily if I replace P with P hat. Now, it does make the approximation a little bit worse, but we're already giving away a little bit. And we're saying that we're happy for it to be untrue alpha proportion at the time. So that is, of course, not exactly but approximately normal 0, 1. At least you would want to check the rule of thumb, which since you don't know P, you would just check N. P hat is at least 10, which is K, and N 1 minus P hat is at least 10. So of course that's K, and this guy is equal to N minus K. So just check at least the number of successes and failures of 10. Once again, rule of thumb. And so your 1 minus alpha confidence interval for P hat would be centered on P hat plus or minus Z, so standard normal alpha over 2. If alpha is 5%, then that's 1.96 times the estimated standard error was P hat, 1 minus P hat divided by N. Now, there's no role for the continuity correction when we're doing this because you're not finding an exact cutoff for K, you're finding an exact cutoff for P. And P of course, in a binomial is allowed to be any real number, so there's no continuity correction to be applied. Okay, but if you want, you know, this is just the first step in a whole lot of more complicated corrections that people have come to find out with a better approximation. But this is the one that you normally first use. Okay, so let's do the Poisson case. Okay. Now, if you just had a single Poisson, that would kind of be uninteresting because your best estimate for lambda is just the observed value, because of course expected, if n is Poisson, then expected value then is lambda. So let's say we have observed quantities x1, x2. So these will all of course be non-negative integers up to xn, which are Poisson with mean lambda. Then x1, here's the key fact that we know, x1 plus everything up to xn is exact distribution. And these are IA. Okay, Poisson n lambda. That's, if you think of Poisson as a limited binomial, that's an obvious fact, or you can check it from the MGF, you can check it a lot of ways. So, so that means, I guess, which is approximately normal mean n lambda, variance n lambda. Remember, variance of Poisson is the same for mean. So that means x bar is approximately normal with mean lambda, variance lambda over n. Okay. So, and then the key thing is, once again, so if n is large,